Okay, earlier on somebody asked me whether you can write these conjugate base acid and base pairs in a slightly different way. And people might have seen that in textbooks where you have, for example, NH3 plus H2O gives NH4 plus OH minus. And what we established is that this is the base. This would be the acid. Now, once it has happened, this would be the acid, and this would be the base. True? So what you can do, and that is very often what textbooks show you, you have base and acid, and you have acid and base. So that's very often how it is depicted. Yeah? So this one and this one is a conjugate acid-base pair. And this one is a conjugate base pair. Yeah? Make sense? Pretty much, I think. Now, I want you to do a few calculations. So the first one that I have for you is, please calculate the pH of 0.01 molar hydrochloric acid. What's the pH of a 0.01 molar hydrochloric acid? It's a very simple one. pH equals minus log 0.01. This gives us negative 2 times negative equals pH equals 2. Okay? That was easy. Okay, now calculate, please, the pOH of a 0.01 molar hydrochloric acid. Ha! Ha! It's going to be 12. You think so?
Yeah, I'm not sure.
Are you sure?
No.
No.
I think we have to subtract it from the beginning. I'm not sure. No? Yeah. Okay, sorry.
Wait a moment. There's a bit something weird here, isn't it? Hydrochloric acid is an acid. The name isn't a clue. So it produces protons. What about the OH minus? Are there any OH minus? Huh. So why does he want me to calculate a pOH? Is that even possible? Of course it is possible. And you were absolutely right earlier. What you need to do in this case is pH plus pOH equals, what was it? 14. So we've just calculated the pH, and therefore the pOH equals 14 minus 2 equals 12. So the pOH of this solution would be 12. How do I have to visualize that? Well, I have 0.1 mole per liter of protons. And at the same time, these protons react with the OH minus in the water and reduce the concentration of the water to 0.00. I just have to internally count. Zero point zero 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 1 mole per liter of OH minus. Which of course is a, oh no, sorry. I did too many. Because it's 12. Which is a pain to write. Do you see how easy it is to make a mistake? But that is exactly the same as 1 times 10 to the minus 12 mole per liter of OH minus. So I can always, using this calculation with pH plus pOH equals 14, I can always convert a pH into a pOH. Okay. Calculate the pOH of a 1 millimolar sodium hydroxide solution. What's that? Sodium hydroxide. What is it? Acid or base? It's a base. Ah, that's good. That's good. You're absolutely right. So it produces OH minus. We don't have to worry too much because we can do it straight away. Right? So what do we get? Sorry? 3? What's your name? Rasheen. Rasheen says 3. Is Rasheen right? Did I say it wrong?
It's O'Shane.
O'Shane. Oh, sorry. Is he right with 3? Yes or yes?
Yes.
I don't leave you any options. Okay, let's see. Why is it 3? pOH equals negative log of, now I have to use this one here, 1 millimolar. What does milli stand for? 10 to the minus 3. So 1 times 10 to the minus 3. Now this molar, that's all right. We don't need to do anything with this molar. Log 1 times 10 to the minus 3. The cool thing is we have minus 3 here, so this is minus 3 negative pOH equals positive 3. Yeah? Are you happy with that? What's the pH of that solution? pH, you are absolutely right, equals 14 minus pOH equals 14 minus 11. Oh, sorry, I was too fast. 14 minus 3, and that is 11. Easy peasy. Right. Now, I have a solution of hydrochloric acid, HCl, strong acid, and this solution has a pH of 5. What is the concentration of the hydrochloric acid? Oh, what a bummer. We can calculate the pH from a concentration, but now it's the other way around, isn't it? Life sucks. How can we do that? Sorry? The reverse of log. Aha. You're absolutely right. What's the reverse of log?
Time is a simple calculation. It's 10 to the power of something else.
You're absolutely right. So, what do we do? And James already mentioned it, but I want to do it systematically. We said pH equals negative log of the concentration of the protons. How do we find the concentration? What we have to do is we have to do the inverse operation. It's a little bit like solving the equation x plus 3 equals 5. How do you solve this equation? You use the inverse operation of plus 3, and the inverse operation of plus is negative. Negative 3. You do that to both sides. You have x plus 3 minus 3 equals 5 minus 3. So the plus and the minus eliminate each other. We have x equals 5 minus 3, and that gives 2. Yeah? By using the inverse operation, we get rid of the thing that annoys us. It's a little bit like in real life. If you want to get rid of your married spouse, the inverse operation of marriage is exactly, that is what you do. Not that I endorse that, but... And in the case of log, the inverse operation is 10 to the power of. Before we do that, however, we need to bring this negative to that side. We get minus pH equals log of concentration. Now we do the inverse operation, and I indicate that like that, 10 to the power of. And what we end up with is 10 to the power of negative pH equals 10 to the power of log concentration. And now we just simply eliminate the things that cause aggro, 10 and log. And what I've got left is 10 to the power of minus pH equals concentration. With or without brackets. Does that make sense? So, I have a pH of 5, pH equals 5. What is the concentration? Of protons? Very easy. We have pH equals minus log concentration. We bring the negative to that side, so we have minus 5 equals log concentration. Inverse operation. So we have 10 to the minus 5 equals 10 and log cancel out, so we have the concentration. What unfortunately we lost in this operation is the unit. What is the unit? Mole per liter. So we probably have to add it here in mole per liter. So it is 10 to the minus 5 mole per liter. That's our concentration. Make sense? pH is 2.3. What is the proton concentration? Now that is something where you need a calculator and a coffee. Oh dear. Yep. Do you get it? So the concentration would be around 5 times 10 to the minus 3 mole per liter. Did everybody get that? Yeah? So you can easily convert these things. By the way, what is the hydroxide concentration? Of this solution? Can we do that? So first of all, we have the pH. Can we calculate the pOH from that? pOH equals 14 minus pH is 14 minus 2.3 equals 11.7. Is that right? And now what I can do is pOH equals minus log of the concentration. Again, I bring the minus to that side. I have minus pOH equals log OH minus concentration. Inverse operation, 10 to the power of, and I have 10 to the power of minus pOH equals 10 to the power of log OH minus. 10 and log cancel out. And we have 10 to the power of minus 11.7 equals OH minus concentration. And that is obviously in mole per liter. Yeah? Can you do something like that? In an exam? In a test? Easy. Right. So we've done 1 millimolar. Okay, let's have a 1 micromolar solution of hydrochloric acid. What is the pH, please? What is hydrochloric acid? Acid or base? Acid. Good. What does micro stand for? So what's the pH? Lisa, what did you say?
I haven't got a calculator.
Oh, you can do that in your head. Minus 6? Minus? I guess positive 6. So you can easily do that in your head. So pH equals minus log of 1 micromolar equals 1 times 10 to the minus 6. This here, if you've got something like that, is very convenient because you just look at this one up here. Gives you minus 6, negative, minus times minus gives you plus, so pH is 6. Okay, happy with that? Straightforward, easy. Okay. We have a 1 nanomolar HCl solution. What is the pH? Loud? 9. Okay. Are you sure? Are you sure about 9? What is HCl? Acid or base? It's an acid. What does pH 9 indicate? Loud? It's basic. Are you surprised? You add an acid into water and it becomes basic. A miracle happened. Or is there something wrong? Do you see the problem? We have an acid, and an acid is always lower than pH 7. So what happened here? Any solutions? Help me out here. What's your name?
Faven.
Faven. Faven, say it loud, because you are absolutely on the right track.
The dissociation of the water.
Dissociation of the water. Ah, does that help us? Every time we work with water, not water, every time we work with water, we have 1 times 10 to the minus 7 mole per liter of protons in it, in the water. So, if I add 0.1 mole per liter of protons to this one, what I have in the water, I have 0.10001 mole per liter of protons. So this one here comes from the acid, from the HCl, and this one here comes from the water. Right? Now, this last one here is just so insignificant that usually your calculator wouldn't even show it. When we add 0.001 mole per liter of hydrochloric acid, we have 0.001 mole per liter. This one comes from the acid. This one comes from the water. It's still not enough to make a difference in the calculator. If we add 1 micromolar of hydrochloric acid, this would be 0.000011 mole per liter. This one is from the acid. This one is from the water. We are getting into a range where the water already might play a role. You see that? If we have 1 nanomolar of hydrochloric acid, we have 0.0000001 1 mole per liter. Now this time, this comes from the water, and this comes from the hydrochloric acid. Does that make sense? So, what is the pH of a 1 nanomolar hydrochloric acid? Can't be 9. Put that in your calculator.
7.
It is 7. Wow. You look at me like I have got 2 heads. A miracle has happened. pH is 7. Because in this case, we can ignore the acid, but not the water. In most other cases, when we have a high concentration of the acid, we ignore the water. In this case, we ignore the acid because the acid is so dilute. Yeah? Does that make sense intuitively? Well, if I have a little drop of water, or a little drop of hydrochloric acid, a tiny weensy drop, and put that in a swimming pool full of water, will it change the pH of the water a lot? Probably not, because it's just such a tiny little bit. It's an incredibly dilute substance. And if the swimming pool was neutral, pH 7 before, it will stay neutral. Yeah? So when we are dealing with very, very dilute substances, we have to bear in mind that the water dissociates as well. This was actually a question on one of the quizzes, and this is going to be a question in your exam. Oh, sorry. You think it was an accident? It was no accident. I could not possibly comment on that. And it's sort of a tradition that I put this question in the exam. The funny thing is, every single year, after the exam, I get an email from several students saying, I don't understand why this is not 9. And I just try to find the emoticon for facepalm. No further comment. Any questions? Go in peace. Have a lovely weekend and be good.